so now I'm going to finish this part with the slides, just telling you of an example of the work that I've done, where I brought together quantum field theory and curved spacetime to, let's say, propose a new sensor. And it was quite bold, because I came up with a proposal that you could use a Bose-Einstein condensate. So let's say the sample itself can be 100 micrometers, 50 micrometers, the cloud of atoms.
Sure.
And the experiment is, again, a tabletop experiment. We could put it in this room, no?
Cool.
And I claim that you could use the BC, because you see an atom, we saw how precise they are. And a BC, you might want to see it as 10 to the 8 atoms cool down to the ground state. So this is a very precise, it's a system that is very sensitive to space-time distortions. And I made a proposal on how could you use the system to detect gravitational waves.
Wow.
That's quite crazy, because gravitational waves are detected in LIGO, where the apparatus measures, each arm 3 kilometers. So this was very bold. And I've been like really kind of, when I met Roger, that was in 2017, I was really invested in that and trying to convince, the community that you need to do this experiment, because it's really opens up a new direction. And Roger was trying to convince me to work on the collapse of the wave function due to gravity. And I was very reluctant, because I thought, no, I want to put my time and my energy into these. And well, after years, Roger managed to pull me more into what he's doing. But yeah. So, well, when you talk about using atoms to measure gravity, what we usually do in quantum technologies is an atom interferometer. So let's say you have a atom and you hit it with a laser, with a photon, and you make the atom, you put it in a superposition of 2 different positions, but they're free falling. So they follow different trajectories, and then you recombine them with lasers, and they recombine at a point. But because they went through different trajectories, they pick information in a phase that depends on the local gravitational field. And this is what a quantum gravimeter is.
Interesting.
And I put here a single particle detector, because although they throw maybe 10 to the 6 atoms at once into the interferometer, all the atoms are independent. And each atom goes through this superposition of trajectories, and then they interfere at a point. So I put here the interference is local, because it's at the point where they recombine. And then this is limited by the time of flight. And the equation is very simple. It's just this equation that's here. Basically, it depends with the time of flight squared, which means the bigger the detector, the more precise it is. That's why LIGO is so big. And they're thinking, because they want to go to, well, LIGO is with light, but the principle is the same. They now want to make a bigger detector in space called LISA to have more precision. So a lot in physics, the tendency is to go very big experiments. Of course, they're very expensive. And my husband says that I'm a rebel, because I if everybody's doing one thing, I always want to do something different. That applies to everything in my life.
Yeah, that's another aspect that unifies us.
Yeah, really? Yeah, no, it's
I'm a contrarian at heart.
Yeah, exactly. So if everybody wants to make big detectors, I want to make them very small and so on. But it has paid off for me in science. Maybe sometimes in life can make me like a Grinch in Christmas and things like that. Because I was like, I don't want to do what everybody does. So socially, I don't want to go to the movie that everybody's watching. But in science, it's been
interesting. Yeah,
it's been good, So well, here I also write that this is compatible with Newtonian gravity, because this is an experiment that is described with the Schrödinger equation. And if you treat the local gravitational field by Newtonian gravity, everything works very nicely. And like I said, these are already commercial. My colleague, Philippe Boyer, has founded a company that he now sold called Mucons. And there are other, like Mark Kasevich does that as well, in which, they build these interferometers, these gravimeters, and they sell them. They're like a meter big, I think, and so on. And that's like, you cannot make them smaller, than that, because then you lose precision. So if you want to get atom interferometers to apply them to fundamental physics, to learn about the equivalence principle, or to measure anything respect to gravity, and so you want to make them more precise, you have to make them bigger. So Philippe Boyer did this amazing experiment in which he put his atom interferometer in a plane. So he flew the plane as well and let it in free fall for a bit to get the long baselines. He also has an amazing experiment under ground called, oh gosh, is it? I forgot the name of it now, but it is like the arms of the atom interferometer are 300 meters long. So this is huge. You can see here sort of the tunnels and so on. And in Germany, you have a drop tower. That is like, what is it like this? Like
a drop tower.
Yeah, so they put up here.
Okay.
Oh, a drop tower. They put up there like an atom interferometer, and then they let it drop to get these long interferometer arms and be able to be more precise. Some other people, also look at these atom interferometries and put lasers and slow down the atoms so that they get, so for example, this paper by Guillermino Tino is really beautiful, trying to miniaturize the detectors. So what I came up with this idea was, well, if you're trying to do interferometry in using these sort of, call it spatial interferometry, because the atom goes through two different positions, the precision is going to be limited by how big it is. So you're going to have to make them bigger to be more precise. But if instead of that we do interferometry not in space but in frequency, then what is going to limit your precision is time. So the states, the sensor can be very small, but you're going to have to produce quantum states that live longer in time. So with this idea that I called frequency interferometry, I came up with a number of sensors, and including the gravitational wave detector. And then I applied it to searches for dark energy, searches for dark matter. I also patented an idea on how to use these states to measure the local gravitational field. So this might have commercial applications in the future. And I like that because I like more fundamental questions. Actually, my favorite question is like, what's the nature of reality? What are we doing here? Where am I?
It's a dangerous question, huh?
Yeah, very. All of these things. But, when you're doing that and you find some interesting things, why not also come up with something that can be patented and commercialized and so on. Then when I met Roger, I was really invested in this. And I'm still working on it. I have some recent results. One of them it was in the old slides. It doesn't matter. But I think I managed to give you a flavor of what you can do by bringing together quantum technologies and apply them to fundamental questions and where things are at. I think I want to finish by saying that this last proposal is an example where we used not quantum mechanics, but let's say a more fundamental theory, because it takes into account relativity, which is quantum field theory in curved spacetime. And although it's not the finished theory, because it cannot address the question of superpositions of mass, you can apply it without problem to specific cases like the propagation of space-time, of packages in the space-time of the Earth, and many other interesting instances. This allows you to come up with, let's say, new sensors. And the theoretical predictions that we've made is that these sensors are so, in principle, they still have to test them, so precise that you might be able to detect a gravitational wave with a tiny system. And these are for high frequencies, by the way. They don't really compete with LIGO, because LIGO works in a different frequency regime. This would be for frequencies higher than the ones that LIGO detects. But let's say, using these patches of the theory that incorporate relativity, I think already show you that you can, in principle, make sensors that allow you to go closer to these scales where I was talking about, that we don't have the guide to unify. No, when people were trying to detect gravitational waves, the first apparatus that were built in Maryland, you can still see them. There are these Weber bars. So people predicted. Weber predicted that the phonons, so the vibrational modes of these big metallic bars, would resonate with gravitational waves. And then he claimed that he actually had detected one. And then this got sort of controversial and then eventually disproved. But actually, the proposal that we made, in which you can implement it by using a BEC and using the vibrational modes, like the phonon modes of the BEC. But because you can cool the BEC to half a nanokelvin, that is 10 orders of magnitude cooler than the Weber bars were cooled initially, then you can prepare the phonons in a highly quantum state, which you cannot do unless you go to those cold temperatures. And then you can exploit all the sensitivities that we were talking about, quantum technologies, to see changes in the space-time. And that's how we came up with that proposal. I think I can talk forever, so maybe it's good to leave it here. I think let's see if I had like some kind of concluding. Well, yes, my concluding slide was to say that I've managed to raise funding to build a new experiment. So I'm working with Chris Boyer, Philippe Boyer and Chris Westbrook, who are going to test some of my predictions in a new proposal that I have for unifying quantum theory and gravity. And we're still working very closely with Roger. So I'm very excited because it's like a new era for me now, being able to work this close with the experiments. And I'll leave it here.
Professor, thank you so much. You've given far more than just a flavor. I lost count of how many pioneering ideas there are here with actual practical consequences in the near term being within a couple of years. I don't recall the last time that's happened on this channel, and all I do is interview people that are at the bleeding edge in their field. So thank you for that.
Thank you. Thanks. Yeah, no, thank you. It's a big pleasure for me to be on your channel.
The pleasure's all mine. Thank you.
Great, thanks.